Welcome. In this video I'm going to show you how you can perform a post-hoc analysis after a goodness-of-fit test using residuals and goodness-of-fit test with Python and my stikpetP library. Now with a residual test, what I mean is that it will simply look for each category and compare it with its own expected count. If you want to do pairwise comparisons, I also have a separate video on that. And also those you can do with a binary test and this one as well. So I have separate videos on that as well. The Python version I'm using is currently version 3.12. And this video will focus just on getting the output. For that I'll need an example data, for which in turn I'll need pandas read CSV. And I'll be loading the general social survey data from 2012, and I adjusted that for some example purposes. I don't actually need all of its data, I just need one nominal field. So I'm going to be using the MAR1 field, which was actually the marital status, as my nominal field. To give you a quick impression, the value counts. So there were 79 people who indicated that they are separated. Now my library is only available via pip install and then the full link to my GitHub and this file. Once you've installed it once, you can load it just as any other library. The function of interest is pH, short for post-hoc, residual goodness-of-fit using goodness-of-fit tests. It only needs the data as input, and if you want you can specify which test it should actually perform, and that could be any of the tests that were also used as a goodness-of-fit test. So either Pearson, Freeman-Tukey, etc. You can also specify the expected counts, so otherwise it will just assume that each category was equally likely. MTC is short for multiple test correction, so that can be any of the ones from the p-adjust function. So that could be Bonferroni, which I think is currently the default, CDEC, Hummel, Holm, CDEC, etc. Quarks are passed on to the function that's being used to calculate each of these. So you can see the individual functions for those if you want more info on that. So let's take it for a spin. The function name, the field, and in this case I wanted to use the multiple testing correction of home. I run this and I immediately get all of this output. It shows each category, the observed count, the expected count, in this case equal because I didn't specify any specific expected counts, the test statistic if applicable, so that means this is a chi-square value, the degrees of freedom, which is the number of categories, -1, but in this case there's actually it's always going to be 1 because this is a goodness-of-fit test, and what it's doing is it's taking this category and just the observed count versus the other categories. Then what we get is the p-value, the adjusted p-value, and the minimum expected count, and the percentage of cells that had a expected count less than 5 and the test used. Now the most likely one of interest is the adjusted p-value. If that's below a usual threshold of 0.05, we would say it's significant, and that would mean that, for example, this one, the E-240, means I need to divide this by 10 to the power of 240, so that's extremely small. So in the population, most likely married will have a significantly different count as the 388.2. This one, for example, is not significant. This one is. So actually all of them are except for never married. If you do have expected counts, like for example you expected these counts and you want to test for that, then you can actually enter those expected counts as a data frame and then add that as a parameter. Alright, I hope this video was helpful and thank you for watching.